Okay. Should be more of you, but maybe the hail made problems.
Oh, really? No, if you were driving? Oh, God.
Yeah. It's pretty bad outside for a minute. So my name is Lee McPherson. This is my second term back, lot in person, so hopefully all the bugs are smoothed out. I know a lot of you guys some of you I've seen before, but some of you are new. Some of you, this is your first time back. Try to go easy on you. I'll try to set all the deadlines very clearly. If there's any circumstances which prevent you from, completing any of the deadlines, talk to me. It's totally, I can work with you. It's okay. So I have been teaching at PCC for, I can't really remember now. I guess this must be my 5th year, because my daughter is almost 5. We moved here when she was born. So I've been teaching here for a while. I taught at Rowan University before that, and I taught at, which is in New Jersey, and I taught at Hillsborough Community College before that, which is in Tampa. So I've been teaching chemistry for a little while now. My degree is in inorganic chemistry. So in case you're curious, that is the last class in chem, if you're a chem major, you'll ever take. A lot of people call Gen Chem inorganic, and there's a little bit of that there, but inorganic chemistry is pretty much once you get past organic is carbon and hydrogen containing compounds. Inorganic is everything else. So it's a much bigger field, it's more complicated, you have to kind of specialize. I'm happy to talk to you about that. If you're curious what else I did, after I did research and I got my PhD, I decided not to do research anymore, and I worked for a company that did consulting for the military. So that was an interesting time, both interesting and boring. Hey, come on in, sit down. Happy to talk about that, and probably the lab is the best time because there's going to be a lot of free time. We're going to be walking around, but feel free to talk to me before and after class too. And say whatever you like in class as well. Raise your hand. Hopefully we can get discussions going again. It was very difficult to do that. Very difficult to do that online. And even last term, when people were a little bit weird about COVID, it was still hard. That being said, if you want to stay distant, it's okay. But let's make it a little noisy. So, I have 4 kids. One of them's still in preschool, so I know how difficult childcare is. If you need help, not with childcare, but if you need help, like with assignment deadlines, for those reasons, that's okay. Let me know. All right, let's talk about the syllabus real quick. If you haven't been to D2L, then this is your first time at PCC. But there it is. I just changed the banner. Pretty much everything that you're going to need is going to be in the content area. And so I've got important docs listed on the side. That's probably where you want to look at first. Class syllabus, that's the link. I've got a few other things here that you can take a look at on your own time. Maybe we'll pull one up. I think only this one's visible for you guys, but it's the lecture schedule. So not exact, but it's kind of here's what I think we'll be doing on those days. And there are reading topics assigned for those lectures. So if you want to keep up with reading, that's one way to do that. And we have 2 books, so both books are listed there. There's also a lab schedule. So your guys' lab on Wednesday morning. We can take a look at that later. And then this is the homework registration PDF. So click on that and please sign up for Master Chemistry as soon as possible. It does cost money, but you can do a free trial, and that will last 2 weeks before you have to actually sign up. So syllabus. I think the main points from the syllabus is that, let's get to the right section here. Come on. I don't want to do this. Okay. I'm in the website version. All right, let's find the right spot here. So these are the books you need. guided inquiry, which is the kind of a workbook packet, and that's going to be our main textbook for this course. I'm gonna basically use that in class. We'll do problems as group from that. So please bring that. The Mastering Chemistry with e-text. So you need that for your online homework. And included with that is an online textbook, which we'll use as a supplementary textbook. So I'm not going to refer to any chapters in that book, but that lecture schedule does have reading assignments, or not much reading assignments, but places to find the topics we covered in class in that textbook as like supplementary. So if you need to read more, please do that. There's a lab manual you have to buy, and that's going to be fun. We're going to do real labs, and the first one's pretty fun. Actually, they're all kind of fun. They're all interesting. We're going to work with LEDs, liquid nitrogen, things like that later on. This last one you don't need. So this book is included with Mastering Chemistry, so you don't have to purchase it if you're fine looking online. But if you need a physical copy, that's it. You don't even need to buy the newest version. You can buy an old version, because we not going to assign specific problems where the page numbers and the problems have to match. So the older editions work fine too. So buy a cheap version if you have to. So there's two types of homework in this class. Mastering Chemistry, online. That's going to be due every Monday, and I believe the deadline is set to midnight. So you have, and that's pretty much weekly. Every week you're going to have a Mastering Chemistry assignment due Monday night, except for the one day when Memorial Day. I made it Tuesday instead. So that's a given, and you actually have an assignment due, two assignments due for Mastering Chemistry due this coming Monday. One is a 221 review, and another one is based on the stuff we're going to go over in lecture today and Wednesday. In addition to the Mastering Chemistry homework, there is a workbook written homework, and I don't have the full schedule set up yet, but there are going to be problems assigned from your workbook packet. You'll have to do them on paper. You don't even have to write on your workbook, by the way. You can keep it nice and clean if you like. You can turn everything on a loose leaf paper if you want, but you can write on it too. The workbook stuff, let me first show you where you can find what is due. So on the calendar here, on the first page, you've got a little calendar on the side. If you don't like this tiny calendar, you can click on the link here and make it bigger. And if you don't like the list view, you can make it look however you want. But this should show everything that's coming up. Now, Mastering Chemistry reminder. This is just a reminder because I can't link it directly. You have to go to a different website, and I can't link the individual problem sets. So this is just a reminder so that in this calendar it says, hey, you've got this due. This is what the workbook homework looks like. So move 1, that's the first one, and you actually have one due next Monday. And this is also going to be due on Monday, but this is going to be due in class. So the deadline is 1 p.m. So before you come in. I gotta turn that off, sorry. Okay. You can see that from Chem Activity 22, you're going to do exercises 1 through 7 and problems 1 through 10. If you haven't used this workbook before, there are 3 different types of questions. There is a CTQ, critical thinking question. That's kind of like interspersed throughout the activity. There is the exercises, which is at the end of the section, and then there's the problems that are also at the end of the section. So make sure you're in the right section when you're doing these. I think the page numbers match up. We did go with a different publisher. They're publishing the same content, so the pages, yeah, that's it. The pages should match up. If they don't, let me know. And here are all the point values assigned with them. And the last part is the most important part, self-grade. Basically, you are in charge of grading your own work. That does mean that you can game the system a little bit, but it's not going to help you to do that, so please try these. You don't have to spend hours on them. If you can't figure it out, you can ask me later, or you can just look up the answer and then ask me why was it this answer later. It's fine. I'm not going to, and so when you self-grade, you're going to use the content area. You're going to use workbook answers and appendices. Here are all of the answer keys for the different chem activity. So chem activity 22, that's the first one you're going to do. And it should show all the answers. Just kind of mark off which ones you got right, which ones you got wrong. And I'm not going to give you the grade that you gave yourself. If you got half of them wrong, you're not going to get 50%, you're going to get the full credit. So it's just a way to immediately know whether you're doing it right or not. And if you are not doing it right, this is your motivation to then ask me later, hey, why am I not getting this right? If you don't do that, I can't help you, okay? So it'll be a big surprise when you do a quiz or when you do the exam. It'll be a surprise to me too, because so talk to me about these things. If you need help with any of this, please let me know. Okay, so those are the two types of homework. The Mastering Chemistry is auto-graded. I will not import that grade into D2L until near the end of class. The workbook stuff is you turn it in. Just turn it in to show me that you did it. That's it. It doesn't have to be completely right. You just have to try it all. Okay. So in addition to homework, we're going to do semi-weekly quizzes. So not this week, because there's nothing to cover. But we're going to try to do weekly quizzes the second lecture of every week. We'll do a quiz at the beginning of the class, and it'll be 15 to 20 minutes long. The quiz will cover the previous week's topics. So we're going to do ionic bonding. We're going to start with metallic bonding as well. So next week's quiz is probably going to be about that. You can probably guess the kind of questions I'm going to give you based on the stuff that we do in lecture. So there'll be clicker questions, there'll be activities you guys do in the workbooks. The quiz will probably follow those types of problems, okay? And we'll try to do at least 5 of them. It depends on how the schedule goes. We won't do a quiz during midterm week. We may not do a quiz after that as well, because it depends on if we've learned anything new yet. But I will let you know weekly if there's a quiz next week or not, okay? So no quiz this week, we'll start next week. And I will drop 1 quiz. So if you screwed up, you're like, this quiz was terrible, I'll drop 1. So the worst one gets dropped. I won't do any makeup quizzes, so if you just not show up for that day, just think of that as your drop 1. And if there's special circumstances, we'll take that into account, so let me know. We're going to have 2 exams and a final. And let's just go right to the schedule so that you can see when they are. Back to important docs. The lecture schedule. So here is, let's see if this works. Oh yeah, that's good. Here is the schedule, and hopefully it makes sense. This is the week that starts April 4th, that's the Monday. We're going to try to do this on Monday, we're going to try to do this on Wednesday. These might shift around depending on if we are too fast or too slow, but here are the reading topics that go along with these if you want to do your reading ahead of time or after, either way. You can see the first exam is the Wednesday, April 25th. And then we have another exam Wednesday, it looks like May 25th. Yeah. And then our final, if I made this, figured it out right, it's going to be that Monday, 6/13. And for all the exams and the final, we'll just do it during the lecture period, and that's it. We won't have a lecture that day. We'll just come here, take our exam, and be done. Unfortunately for you guys, the exam is right after lab. So, but you'll have a 2 hour break, right? So it's 1 hour break, sorry. 9 to noon. Okay.
So it's going to be a lab final and then the final?
No, there's no lab final,
Okay.
just a final, yeah. And chemistry exams are cumulative, so I'm not going to do it on purpose, but you're going to have to understand metallic bonding to be able to do some of the later stuff. Well, actually, some of the stuff is not super cumulative. Chemistry 221 is really cumulative. This was a little bit more topics separated, so.
Are there any particular note types or books, or is it going to be open book or notes available for these exams or finals?
They are not going to be open book.
Okay.
Or open note.
Okay.
What I will provide you with is a big equation page.
Mm-hmm.
You don't have to memorize equations. I don't believe in that at all. You do need to start knowing some of the polyatomic ions. And I didn't force my class in 221 last term to memorize them outright, but you're going to start seeing them often, and it shouldn't be the thing that trips you up. But equations and constants, all that stuff, I should provide it to you. All right, so you need to know how to use them. You need to know what they mean. You need to know what this variable is, for instance. But and conversions, so how to do an electron volt to a joule kind of thing, I will give that to you as well. The only conversions you absolutely need to know are prefix conversions. So what is a nanometer to a meter conversion? Things like that. All right. Now, I'm going to bring this up now. We could talk more about the lab in lab, but the lab is graded separately at first. So we're going to so lab is a big part of this course. You'll have to do the lab, and you'll have to get a grade of 70% or better in the lab portion of the exam in order to pass the course at all. And again, I'll talk more about the lab on Wednesday morning. Kind of show you the format, what it's going to look like if you haven't seen it in a while. It's going to be similar if you've taken the online stuff, the remote stuff. It's similar. We didn't change that much, other than just giving you videos to watch. But as far as what you have to turn in, it's similar to that stuff. So I'm going to leave this for Wednesday. But I just want to make sure you understand that even though we have an overall average grade that's going to be on D2L, I have to look at the lab grade separately first to make sure you got a 70% or better in that, and then I will include it for the whole class. We don't drop any labs, so try not to miss any labs. Again, special circumstances, we can figure things out, but let me know. All right. I think this works out still. This is approximately how you can think about so the totals are set. Notice that the lab is worth 20% of your overall grade. Your quizzes are about 8% of your overall grade. The other two exams, 20% each. Your finals, 20%. So the labs and the exams are 80% of your grade. The rest of it is quizzes and homework. And I kind of wanted to do percentage each. So this is kind of hard to figure out, but at least for the quizzes. Each quiz, if we drop one, so you only count 4 of them. Oh no, I didn't do that right. I divided 8 by 5. Anyway, it should be 2%. That's why I messed it up there. So each quiz is about 2% of your overall grade. So if you miss, besides the dropped one, if you miss another one, that's 2% of your grade automatically gone. So don't miss a quiz. Don't stress out too much if you don't get a great grade on it, but it's going to limit your ability to get an A if you keep, doing badly on them. So try to prepare ahead of time. Okay. I realize I don't have my office hours up here, I don't think, but I'll let you know what those are in a second. This is the straight letter grading we're going to use. There's no plus or minus, so if you get 89.5, I'll round it up to a 90, and you get an A. So my office hours are officially going to be Monday and Thursday, 10 to 11 a.m. And they're going to be in room 307? Is that where our lab is in? There are labs in 306. Okay,
yes,
so 306. So since there's a lot more faculty in this office, I can't have all of you guys visit me over there. So we're going to go visit in the lab room, which is empty. So what does that mean? Well, I told this to my last class. I'll probably be here 8:30, and I'll have the whole morning to do grading and stuff. This is officially when I'm supposed to be there, but if you try to find me before then or after then, I might be there too. So don't be afraid to email me and say, hey, can I come earlier or can I come later? Just give me some time to eat lunch. Go to the gym. That's open, by the way.
Oh, really?
Limited hours during lunchtime.
Oh, that's gonna help me out though.
Yeah. And the testing center is open. So for people who have signed up for accommodated testing, you can reserve time for your exams. And you can talk to me about that if you need to afterwards. As far as quizzes go, I will talk about that with people individually if we need to. All right, so the rest of this is kind of boilerplate, just kind of strict rules about all the stuff. I let you guys read that yourself. Any questions about the way the class is going to work so far?
So just to be clear, the pre-lab workbook homework and workbook homework answers are on Wednesday. Are due on Wednesday.
Oh, yeah, well, so I haven't talked about the lab stuff. But yeah, the lab stuff is all going to be due during lab.
Yeah. And the workbooks are due on Wednesday.
No, I think everything's going to be due Monday.
Oh, okay.
Yeah, all the regular homework's Monday, yeah. So the quiz is going to be Wednesday. Yeah.
So we drop off the workbook stuff when we come in. We drop off the lab stuff when we come in, and then the master chemistry is due Monday night.
Yes. Yeah. Okay. I used to have this office all to myself, and then I got to share it with people. It sucks. Anyway, it's weird hearing other people. All right. We talked about that. Okay, so we're going to use clickers every day here, and I guess, one, two, three, four, five, 6. Well, it should be enough. If you guys want to grab a clicker, it's nice to kind of keep your attention because what's the word? Engaged. That's it. I would make this a habit unless we're doing an exam. But grab a clicker on your way in. We have wipes everywhere, so if you're worried about anything on the clickers, please wipe them down. Treat it like a lab. Trust nobody. Assume the last person was disgusting, and if you want to wipe it down, go for it. As far as I know, though, COVID doesn't transmit very well with hard surfaces, so I think it's okay, but leave it up to you. We're going to return these every day, so make sure you put them back later. They have numbers on them, so make sure it goes in the right spot on the box. And let me turn this on. Oh, come on, why doesn't this work? All right, I got to fix this later. There we go. I'm curious what happened with your last 221 class? Whether it was here, whether it was somewhere else, how long ago was it, or none of these fit you?
Can I redo it?
Yeah, you can change your answer.
Okay.
Yep.
Alright, redo one.
Unlike the Zooms thing, which you can't change. If your thing is blinking red, then it's not synced up with the little clicker thing. And I can fix that. And if it's got a low battery warning, let me know. But it should be okay. All right. So this is kind of what things look like. Oh. All right. so, wow, okay. So,
Oh, that's gonna be interesting.
this is gonna be
This
really
is gonna be really
crazy.
interesting.
So I want to warn you guys that if you didn't take chemistry here at Sylvania, I forgot which other campus mimics ours. I think maybe Rock Creek. But the other PCC campuses do the 220 series in a different way. So ours is atom first. We kind of start with the basics of the atom, and then we kind of build up from there. So 221 is all about understanding the atom at a really, really high detail level. And then now we're doing bonds. We did covalent bonds at the end of 221. Now we're going to do ionic and metallic. So if you came from a different campus, you may have kind of covered some of the stuff we're going to cover now. You may be like, I don't know what's going on. I haven't seen this before. If that's the case, speak up and let me know. Hey, I don't get this. We can go over it.
My mouse in here, sorry.
No problem. And obviously, if you haven't done chemistry in a while, well, that's gonna be another roadblock. Not a roadblock, but a handicap. It's gonna make it things difficult. So let me know. And I'm not sure. I was trying to think, well, what would fit? I mean, maybe at a different college altogether. But this is gonna be interesting because I was hopefully expecting most of you to be in this one, but it's only 2 of you. All right, that's okay. We're going to have an interesting time. I will try to go slow as a result. So here's what the textbook kind of looks like. Again, don't buy it unless you absolutely need a physical copy. But you do need this, and it doesn't look like that anymore. It looks a little different because we have a different publisher now. But the Mastering Chemistry, I think this price still works. It's a little bit cheaper if you buy it directly from Pearson. So, if it's not too late, I would try that. But I put this in to remind myself. If anybody's good at taking notes, there are people in this class that need notes, and they do it through the disability services. So if you want to provide your notes, I think you can get compensated for it. It depends. I've heard cash. I've heard gift certificates to the bookstore. Could be voluntary too. I don't know.
I'll throw myself underneath the bus. I signed up for that. Because I have motor issues, and so I can take notes. But if you go on hardcore tangents for 40 minutes, my hands and my brain just start.
Yeah.
I have to put it down and just kind of focus. So I'm trying that service out this year.
Okay.
It's really cool.
So if anybody takes good notes and want to try to get compensated for it, might as well just tell them you are taking it for this class, and other students will appreciate it. Okay. So here's kind of what we're going to do this term. So in 221, at least in my 221, the last thing we went over is covalent bonding. So how electrons are shared to make these bonds called covalent bonds. We looked at valence bond theory, how the orbitals overlap and made those bonds, things like that. So we're going to kind of take the next step further. We're going to talk about molecular orbital theory, which I talked about in my class, but we're going to do that again from scratch. We're going to talk about the other kinds of bonding, ionic and metallic bonding. Metallic bonding is crazy. We're going to then get into just kind of how solids form and what solids kind of look like. It's not as cut and dry as you might think. We're going to just brush the surface of crystallography. And then we're going to talk about intermolecular forces. Big, big deal in organic chemistry, a big, big deal in biochemistry. And then once we get through that, we'll talk about liquids and then gases. Once we get through all that, that's one section. We're going to switch over to reactions. So instead of just looking at compounds and how compounds, molecules interact with each other, we'll look at the reactions themselves. We'll look at the energies of reactions. So a little bit of thermodynamics. And then if we have time, we'll do kinetics, which is rates of reactions. But if we don't, that'll be in 223, if you take 223. Okay. Yeah?
Do you go over thermodynamics?
A little bit, yeah. So that's what
that's
this
gonna
is.
be in there.
That's what this is going to be.
Okay.
Energy reactions.
That's
Yeah.
what I thought.
Just we're going to do a little bit of thermodynamics. 223 is going to do more of it.
Okay.
Yeah. Okay. So the ionic bond. Oh, yeah. Question. Sorry.
I was just asking about office hours, if you ever like do anything over Zoom.
I can. Yeah. That's totally fine.
I'm 20 minutes away, so driving there and driving back to try to.
Yeah. So email me and we can set it up. Yeah. Okay. So I've been hinting at this in my 221 class for my students, throughout the class. We're gonna kind of understand how ionic bond forms. So if you can look at the progression from a regular non-polar covalent bond, you have these two atoms that are overlapping their orbitals and sharing electrons. If you replace one of those atoms with a more electronegative atom, so you start to have this imbalance of sharing. The more electronegative atom will kind of have the electrons that are shared hang around it more than the other atom. And so you'll start to build up a partial negative charge. That's what that symbol means. That's the Greek lowercase delta, partial. And as a result, the other atom gets a partial positive charge. That's a polar covalent bond. So again, the electrons are still being shared. But sometimes that electronegativity difference is so great that instead of being shared, the electrons are just completely ripped away from the other atom. And so now that one electron, in this case, is hanging around this atom only, and that's why it has a full -1 charge from that electron, and the other atom has lost the electron, so it's got a +1 charge. This is an ionic bond. So, let's kind of review from 221. In 221 we talked about this model called the core charge model that helps us understand how attracted valence electrons are to the atom itself. And we do that by looking at the nucleus of the atom and the inner electrons together as a core. And the way we calculate that core charge is we look at the nuclear charge, how many protons does it have, and we subtract the number of inner electrons. So not the valence ones, the outermost ones, just the inner electrons. And that gives us a core charge. So here is the shell model for oxygen. This is the, hey, here's where the electrons are. We have two shells. Shell 1 has 2 electrons in it. Shell 2 has 6 electrons in it. If you need a reminder of how to do that, you can look at the periodic table. So period 1 has 2 atoms in it. That's a reminder that shell 1 only has 2 electrons in it. Shell 2, period 2, has 8 total elements in it. That's a reminder that you can have 8 total electrons possible in shell 2. But when we get to oxygen, we get only up to 6 electrons. So 1, 2, 3, 4, 5, 6 valence electrons. That's the shell model. The core charge model is to combine the nuclear charge, that +8 nucleus from all the protons, minus the 2 inner electrons, and you get a +6 core charge. If you had more inner shells, you would include all of them. All right, so just don't include the valence shell. That's your valence shell, your outermost shell. So what does this tell us? All right, this tells us that these outer electrons are approximately feeling a +6 charge. So this attraction that each electron is feeling is up to a +6 positive charge, which is a very strong attraction versus something like a +1 core charge. Okay, so let's open up our workbooks. You know what? I forgot to print them out. That's what I forgot. So here's what we'll do. We'll do it on the screen. We're gonna, because I did say you didn't have to buy them today. So we're gonna go straight to Chem Activity 22, and we're gonna look at CT questions 1 through 4. So let's do that. So this is what Chem Activity 24 looks like, and so there's a little bit of intro, and this is where you kind of read a little bit. I think I kind of introduced this well enough, so hopefully we can skip it for a second. And here is the critical thinking questions, CTQ questions. Number 1, so we'll do it all together since some of you guys, most of you don't have this yet. When an ionic bond is formed, what type of atom is likely to lose one or more electrons or gain one or more electrons? So, in terms of relative electronegativity. So, remember what electronegativity originally means. Electronegativity is a measurement of attraction to shared electrons. So really electronegativity is really for covalent bonds. But if you've got an atom that is very electronegative, that means it's very attracted to shared electrons. It really likes to have extra electrons. It will attract them. It will have those electrons hang around itself more than a less electronegative atom. So if you're talking about an ionic bond, the atom that's going to lose the electrons is going to be the atom that is the least electronegative. Right? The one that is the most electronegative is going to be the one that gains the electrons. It's the most attracted to electrons. Does that make sense? Yeah. So NaCl. This is our standard table salt. Sodium is a metal. Metals have low electronegativity. So remember the trend for electronegativity. Fluorine is our most electronegative element on the periodic table. We're going to ignore the noble gases for now. And as you go up and to the right, you get more and more electronegative. So down and to the left, least electronegative. So to the left, those are all the metals. Down to the left, most of the metals. So metals are least electronegative. Chlorine is pretty close to fluorine. This is the most electronegative. And so in terms of which one's going to take the electron, it's going to be the chlorine. Chlorine's going to take the electron. Sodium is going to lose the electron. So determine the core charge in valence shell for sodium and sodium plus. All right, this is a good one. It's good review for like 221 stuff, and if you didn't do the 221 that we did, this will help as well. So Na. First, let's do the shell model. So Na has 11 protons. It's atomic number 11. So it's got a plus 11 charge at the nucleus. And we can just look at the periodic table to look at like the numbers of electrons in the shell. So first shell has 2 electrons in it. The second shell, so period 2, that's not where sodium is. Sodium is in period 3. So period 2 has all of its electrons. There's 8 of them. 5, 6, 7, 8. Where I draw them exactly on this circle doesn't matter, as long as they're on that second shell. And then period 3. So sodium is the first element of period 3. So it's only going to have 1 electron in that third shell. This is the shell model. Now we're going to switch that into a core charge model. So let's just calculate the core charge. We're not going to draw the whole thing. But what is the core charge? Well, there's 11 protons at the nucleus, and there's 10 inner electrons. This is our valence shell, which has 1 electron in it. Everything else is an inner electron. So 2 plus 8, 10 inner electrons. So the core charge is plus 1. So again, what does that mean? That means that this outer electron is feeling a core charge of plus 1. So it's not feeling a very strong charge. It's only a plus 1 charge. Let's compare that to sodium plus. All right, so sodium plus is the ion form of sodium. It's going to have a very similar shell model, except a plus charge means it's lost an electron. Electrons are negatively charged, so it's if it's a plus, it's lost a negative. And it's going to lose the easiest to remove electron. It's going to lose that outer electron. That's going to be gone. So when I do the shell model for sodium plus, it's going to have its 11 protons in the nucleus still, but it's only going to have 2 shells left. That third shell is empty, so I'm not going to draw it. 6, 7, 8. And now when I do the core charge, well, the rules for core charge is number of protons minus inner electrons. Well, this is our new valence shell. The valence shell is defined as the outermost shell with electrons in it. That's shell 2 now. So I cannot subtract these electrons from as an inner electron. These are not inner electrons anymore. These two are. So there's only 2 inner electrons. So the core charge of sodium plus is +9. So what does that mean? Well, based on your answer from part A, which species will it be easier to remove an electron, Na plus or Na? Well, to remove an electron from here, it's going to be one of these in the second shell, and these electrons are each feeling a +9 core charge, a very strong attraction, a +9. Whereas this outermost electron here is only feeling a +1 core charge. So that electron is the easier one to remove. Okay? So when we think about sodium versus sodium plus, only sodium really can lose an electron easily. Sodium plus is very, very difficult to remove another electron because the rest of those electrons are held on with a much stronger core charge. All right? So the ions formed in molecules from group 1 atoms, which is the alkali metals. Sodium belongs to the alkali metals. They only make +1 ions, not +2. Well, that should make sense to you at this point. You can lose one electron pretty easily because that electron is only being held on by a +1 core charge. If I try to remove a second electron to make Na2+, it's extremely difficult to do that just based on what the core charge is. And so group 1 metals really only make +1 ions. That's it. Okay. So we can look at the same concept using group 2 atoms. How do we figure that out? Well, let's do a quick one, magnesium. So magnesium has a +12 charge at the nucleus, atomic number 12. Pen look better. Let's see if that looks better. That's better. Okay. The other thing, I was the only class in here, so the boards were nice and clean. Now they're dirty. All right. So it looks like sodium's a little bit, except 2, 3, 4, 5, 6, 7, 8. The third shell has 2 electrons in it, not just 1. That's magnesium. So if you do the core charge, we're going to do the +12 nucleus minus the inner electrons, which are 1, 2, plus 8, 10 total inner electrons. So there's a core charge of +2. Right? These are the valence electrons. We don't subtract those. Those are the outermost electrons. So the idea is, well, if I make magnesium plus, I'd remove this electron. The core charge would still be +2, because it would still be 12 minus 10. So if I removed a second electron, I would make Mg2+. Now what would the core charge be? Well, if I removed these two, that's now no longer the valence shell. There's no electrons in it. The valence shell is this one now. And the core charge would be 12 minus 2, which would be a +10. So you stop at magnesium 2+. You can't remove any more electrons after the second. Yes?
So, all the electrons in the, in like the outermost shell, they share the co-charge. It's not like each electron has a specific core charge.
Yeah, so when you, so what we're doing is we're using Coulomb's law, which if you haven't taken our specific 221, is a very simple equation. It compares, or looks at the attraction between 2 charged particles, only 2. And so the first one is going to be the nucleus, or in this case, the core charge, like the combination of the nucleus with the inner electrons all together. And the other particle would be 1, of the valence electrons. So yeah, if for Mg, regular Mg, this electron is feeling a +2 core charge. This electron is separately feeling a +2 core charge. Yes. So you can only do two at a time, two kind of things at a time.
This is kind of a weird question, but like, okay, so I remember when we were originally learning chemistry and we were learning about charges and everything like that. I remember you originally said something like these are like their natural, like more common states.
Yes.
So like salt in salt mines, is that just NaCl? That's not just pure NaCl, right? I guess my inevitable question is, does nature naturally stabilize the cores and the electron balances of most elements, I guess, in nature? I mean,
so
like if I pick up Na, or if I go find NaCl, or if I go find Na, is Na naturally in a +2 charge in the wild, or is it something that has,
+1. It's
or +1?
Yes, so yes, it's almost always, so for sodium, it's almost always going to be a +1 cation. Sodium metal exists, but it's super reactive. It will react with anything nearby and make these sodium cations.
Because it's removing so much energy from natural, like just natural
Well,
balancing.
so the nature of matter is it wants to be, of everything, it wants to be in the lowest energy state possible. And I'll say this, if you have a sodium atom in a vacuum versus a sodium ion in a vacuum, I believe the sodium atoms are typically lower energy. But if it's nothing's in a vacuum, nothing's by itself, in an environment with other things, sodium ions paired up with a chloride anions is lower energy than a pure sodium atom.
Okay.
Yeah. Yeah. So at least for the alkali metals, you're almost always going to find them as cations. Yeah. Yeah. All right. So all we're doing here is just kind of giving you the basis for why you've memorized these charges. Why is everything group 1 +1 charge? Why is everything group 2 +2 charge? Well, these are the reasons. So we're going to do the same thing for fluoride real quick. Fluorine, fluoride. Again, this may be just review for you, which is fine. Go slow a little bit. Fluorine versus fluoride. So the shell model for fluorine. Oh, actually, let's do fluoride and F2-. That's what they wanted to do. So F- is 9 protons in the nucleus. And then fluorine normally has 9 electrons, but we're going to do a 10th electron. That's where the minus charge comes in. It's an extra electron. So 10 electrons, we'll put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the core charge for this is going to be the 9 minus the inner electrons. There's only 2, right? This is the valence shell, so the inner electrons is everything else, plus 7. So these valence electrons each feel a +7 core charge. If I combine these electrons and these protons together into one blob, that blob, whatever it is, that core has a +7 charge. It's just a tool we use, again, to kind of facilitate thinking about how attracted those valence electrons are. So that's F-. If I did F2-, that's 2 extra electrons. So 11 electrons. Well, we're going to have a +9. We're going to have 2 here. Have 8 here. 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. And then the 11th electron doesn't fit in that second shell anymore. The second shell can hold 8 electrons and that's it. So the 11th electron has to go in the third shell. That's where it would go. So what would the core charge now be? Well, 9. But now our valence shell is shell 3. So the inner electrons, there's 2 here plus 8 in the second shell, 10 total inner electrons. That's weird, a negative core charge. So what would that mean? This valence electron is being repelled by an equally negative charge, right? 2 negatives will repel each other. So there's no way you can make F2-, at least according to this model that we have. Alright, if you tried to make F2 minus, that outer electron is repelled by the core charge there. Two negatives will repel each other. So this is the max. You can make F minus and that's it. You don't make F2 minus. So group 7 elements tend to make -1 anions, and that's it, -1. So you can use the core charge concept to kind of understand a lot of this type of ion charge. Kind of answered B there. So C, and it's pretty much the same for every atom down group 7. If we do the same for chlorine, it'll just be a lot more electrons, but you'll get the same core charge. You'll get a +7 core charge for Cl minus, and then if you tried to do Cl2 minus, it would be the same as F2 minus. It would be a -1. It works out that way. Okay, I think that's it. Yeah. Okay. So hopefully, if it wasn't review, you're like, it's not too much to follow. So what is the most likely ion form for iodine? Feel free to use the clickers if you've got one. Pick one up. Did we run out of clickers? Maybe I should put it on the box out. Anybody need one?
Actually, here, funny. I still have this. I use this since the first day that you gave that we made it. It's the best one that I made.
Good. Yeah. You're not gonna be able to use it for an exam, so.
No,
you
but I
use
just,
it.
it's the only one. You go online. You try to look up all the ones. There's so many ones that are just useless or
Too much information or too little.
Yeah.
Okay. So for this one, most people answered C. So iodine is group 7. You don't have to do this kind of complicated, this is why it's this. Just memorize, hey, anything 1 over from the noble gases is going to generally have a -1 charge as an anion. Anything in group 6A, 2 over from the noble gases is going to have a -2 charge. Anything in group 5A, 3 over from the noble gases is going to have a -3 charge. These are the nonmetals. The metals are going to have positive charges generally. So group 1, +1 charge. Group 2, +2 charge. Group 3A, starting with aluminum and gallium and indium, although they're a little bit funny, have +3 charges. So why did I skip from group 1 all the way to group 3, or group 2 to group 3? Noble gases are really funny, or not noble gases, transition metals are really funny. They are not as regular, let's put it that way. If you like foreign languages, there are irregular verbs in chemistry, okay? You can't predict them as well. Now, that's not to say that you can't predict anything. You definitely can predict stuff about them, but it's not as simple. Okay. So, I guess, why is it working now? That's weird. So what are the charges for the ions formed by sodium and calcium? Notice that the symbols aren't there. You guys know what the symbol for sodium is, hopefully. I think the British, we used to call it natrium. Na. Please get used to these symbols. All right. All right, so we've got a bunch of different answers. So sodium is Na, that's number 11. Magnesium is Mg, number 12. So if they are going to form ions, it really keeps turning off this way. They are going to form ions. The ions they're going to form are going to be, and I erased sodium, but it's going to be +1, and the magnesium is going to be a +2. Because once you remove that second electron, you can't really remove any more. If you try to remove a third one, well, you can't remove the third one because the core charge now is plus 10. That third one is really well held on. So, again, don't memorize this explanation. Just memorize the fact that it's group 2. Group 2 metals will have a plus 2 charge. Group 1 metals as cation will have a plus 1 charge. So it's B. Okay. The other thing I want to remind you is, this is actually intro chem stuff, but people forget this. When we talk about ionic compounds, we do not talk about molecules. Alright, so an ionic compound, you don't say sodium chloride molecule, because it doesn't exist. There is no single Na and Cl together and that's it. They come as these extended structures. So an ionic compound, the formula NaCl refers to the ratio of atoms, that's it. There's 1 sodium for every 1 chlorine, but there's tons of them. So, that's ionic compounds. Covalent compounds are molecular, and we're going to say that a lot. We're going to say molecular compounds, and we're referring to covalent compounds usually. They do share bonds, and so you specifically have a certain number of atoms that make up these compounds. So they make molecules. Now, we have learned in the past that covalent compounds are formed from 2 nonmetals. And we learned that ionic compounds are formed between a metal and a nonmetal. That kind of holds true, but not completely. If you took 221 with me or anything similar, and you started learning about polar covalent bonds, maybe you saw this little this diagram where you look at the difference in electronegativity, and if it's a really large difference in electronegativity, it goes from non-polar covalent to polar covalent. But then if the electronegativity gets even bigger, it switches from polar covalent to ionic. So we're going to see lots of gray areas in this class. Alright, so we're going to stop thinking in terms of concrete, hey, metal, non-metal is ionic, non-metal, non-metal covalent. Yeah, that's true, but that's boring. We're going to look at the more interesting things later. So I just want to keep that in mind. Let's look at ionic compounds a little bit more generally. They follow the octet rule generally. That's kind of how these ions form. They have eight full electrons in their outermost shell. Whether they have to lose electrons to do that, like a cation, or they gain electrons to do that, like an anion. They're almost all solids at room temperature. There are a few liquid ionic compounds. They're called ionic liquids. They're really weird. I did not bring any, but here are some ionic compounds. This is a giant crystal of sodium sulfate. Here's another one. I don't know why it's not in the jar. It's not toxic. And this is just, I think this is just pure table salt, just grown in really large cubic liquid crystals. There's another box of them, or another thing of them. This is boring nickel nitrate. It's a nice color, but it's giant crystals. I don't know what to do about passing these around because of COVID, but if you want to come and grab them, go ahead. It's fine. I'll just leave it there. Please, I don't mind people walking around. If you have to leave for a short term, I don't care about it either. Don't worry about it. So they're generally solid. That means their melting point is pretty high, but it actually can range quite a bit. So they go from 500 to 3,000 degrees C. Now, how they form is a lot of ways. You can form sodium chloride using pure sodium metal and chlorine gas, although this isn't true chlorine gas, it's just the atom. And if you do that, the sodium will give up its electron to chlorine. You'll make the cation and the anion version in large numbers, and you'll make this stuff. But it doesn't have to form like that. You can already have sodium ions. You can already have chloride ions from other compounds, and they can get together too. So there's lots of ways to form this. But I guess this is kind of exciting. So let's do this.
Oh, cool. I was just thinking that. I was going to watch this.
I mean, we can't do this in person. Not easily. commercials.
And I've been working.
You know what? This is a boring version. Oh no, maybe it's not.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
All right. So, oh, that's not it.
This video is an introduction to
Whoa.
ionic bonds and ionic bonds. Don't know anything?
Excellent. All right. So, let's talk about that ionic bond. And if you've done anything with Coulomb's law, it'll be pretty clear how an ionic bond is formed and how it works. But let's just remind people what Coulomb's law is. Now, the version we're looking at in this class is a little bit different from the version that we looked at in my last class. In the last class, we used a version of Coulomb's law where you're calculating energy, potential energy. So on the left side of the equation was a potential energy term. So in this version, we're not looking at energy, we're looking at force. And the only difference between them is with energy, we had just d in the denominator, the distance between them. With force, it's the distance squared. That's the only difference. But the values, the signs mean the same thing, okay? What this is saying is you look at the charge of one particle and the charge of the second particle, and you divide that by the distance between them squared. And that tells you the amount of force between those two particles. In this case, a negative force is going to be an attractive force. Yes?
Is the force equal to that, or, I mean,
Oh.
is force equals negative that, or is
So,
force minus?
oh, I'm sorry, here it is. Sorry, I guess in this case, the positive force, this is a force of attraction, so we're automatically making it negative. Okay.
So you're saying the force is negative? It's negative.
Let me restate. I stated it wrong. So, first of all, this sign here means proportional to. So it's similar to an equal sign, you can replace this proportional sign with equals with a constant. But that's all that means. Think of it like an equal sign a little bit. So if you have, for instance, a proton with a +1 charge, or a cation with a +1 charge, and an anion with a -1 charge, you'll get a negative sign, plus and negative. You'll get a negative sign in your numerator. This negative cancels out that negative, and that will give you an attractive force. Okay. The distance between them will also affect the amount of force, and so the smaller that distance between them, the stronger that force is going to be. All right. So if you make this denominator distance very, very small, making this denominator very small will make this overall term very, very big. So that's basically Coulomb's law. We used it for looking at how an electron is attracted to a proton, the nucleus. So we used it last term for understanding how an atom works, just in general. But you can also use it to understand how an ionic bond works. By looking at, hey, you have a cation like sodium with an anion like chloride. So there is a plus charge, there is a negative charge particle. And we just need to measure the distance between them, and we can calculate the force between those two. So again, this was what we did last term. So there's potential energy is equal to some constant, charge between the distance between them. We're switching it up to, instead of potential energy, we're looking at force. That's it. The only difference is there's a squared term here, but they kind of mean something similar. Okay?
Sorry, there's no negative sign for that.
Yeah. So I think in this case the K has a negative sign incorporated into it. So this K and this K I think are different. I'm pretty sure are different. And if you need to understand how are these related, like.
Oh yeah, because he has a constant, right?
Sorry?
Coulomb has a constant, right?
Well, a Coulomb?
Yeah, like this one has a constant, right? Coulomb's law, the equation.
Oh, Coulomb's yeah. Coulomb's
okay.
law. Well, so okay, in almost any equation, the constant in the equation is used to convert units.
Yeah.
So up here, this constant was used to convert between relative charges. So if you put a +1 and a -1, that's a relative charge, into energy, for instance. But you can use a charge that uses a Coulomb charge, and then you have different K. So the K depends on the units you're using.
Okay.
But anyway, how do we go from this to this? How are they different? Well, this is a physics equation. Energy is a force times a distance. So I can replace this energy term, this potential energy term, with another force and another distance, and you get the same kind of equation. So this is just, hey, this translating what we learned in 221 to 222. It's the same equation, just a little bit different. Okay. So we're going to use that and understand a little bit of ionic bonding. Here is kind of a three-dimensional network structure of sodium chloride. And we're actually going to look at a lot more different ionic compounds and a lot more different structures later on. But before we get to that, let's just understand basic ionic bonding. Which one is the sodium, which one's the chloride, what forms when magnesium and oxygen react. And we're going to look at the difference between the ionic bond strength between sodium chloride, sodium fluoride, magnesium oxide, and magnesium sulfide. So that's the whole point. We're going to understand what these answers to these questions. So, and I guess we'll do it on the board again since we don't have copies of this. All right. So there's that explanation again. Here is this thing. So number 5, what are the charges on the ions? Well, we already know this. Sodium is going to be a +1. So even though it's not written, we know this is an ionic compound because they get metal with a non-metal compound. So how do you make those into a compound? They have to be ions. And sodium generally is going to be +1. Chloride is going to be -1. We know that from where they are on the periodic table. Now, in figure 2, we've got 2 different types of ions. Which ones are chloride and which ones are sodium? So this comes back to 221 periodic trends. So this one's apparently is a little bit easier than most. they're both on the same period. They're both period 3 elements, sodium versus chlorine. If we were looking at the neutral atoms, just neutral atoms, well, as you go from left to right, things get smaller. So sodium atom, regular neutral sodium atom, is bigger than chlorine atoms. But we're not looking at the neutral atoms, we're looking at the ions. So what happens when sodium forms an ion? Well, it loses an electron. And notice where that electron comes from. It comes from the shell 3. And now shell 3 is empty. So how do we determine the size of an atom? It's by how far the electrons go. Well, now it doesn't have an electron in shell 3. The outermost electrons are in shell 2. Sodium ion is going to be a lot smaller than normal, than regular sodium. A lot smaller because it's lost a shell. Chloride versus chlorine. So chloride, Cl minus, the anion, has gained an electron. What happens when you add electrons to the same shell? What's the force that causes things to happen? Like, does it get bigger or smaller, first of all?
Bigger.
It gets bigger, and the reason it gets bigger, so more electrons means more electron-electron repulsion. So nothing's changing, the protons are staying the same, you're adding electrons to the same shell, so you're not getting to a bigger shell. So really the only way we know it's getting bigger is there's more electron-electron repulsion. These electrons that are in the same shell are repelling each other, causing them to be a little bit further away from each other than they normally would be. So chloride is bigger than chlorine, right? Anions are generally bigger than the neutral version. Cations are smaller than their neutral version. So cation, sodium plus, is going to be smaller than Cl minus. So the gray ones are the sodium pluses, definitely. There's going to be cases where it's a lot harder to tell. And you'll have to look at a table to look at what the actual sizes are. But this one's pretty clear. Sodium plus is a lot smaller than Cl minus. So what is the charge on the cation form for magnesium? I should use the black one. This one's a bad one. Keep migrating my erasers to the wrong side. Well, we've done this one. Magnesium is what? What charge is going to be?
+2.
+2, yeah. It's group 2 on the periodic table, so as an ion, it's going to make it +2. And then oxygen, 2 minus. So it's 2 over from the noble gases, and it's a non-metal, so -2. Notice we always, as when we write charges, we write the magnitude first. So if it's not 1, you can leave 1 off, but if it's more than 1, you write the magnitude, the size of the charge first, and then the sign second. I can't exactly tell you why. It's just kind of things we've done. Writing +2 means something slightly different in chemistry.
What does that mean?
When I see it, I think of oxidation state, which is a different thing.
Different branch.
Let's stop talking about that now. but if you did write +2, I'd be like, all right, I understand what you mean. But normally we write it as magnitude, then charge. Somebody screaming out there? All right. What is the formula for the ionic compound containing magnesium ions and oxide ions? So this is basically how do you write the compound with magnesium and oxygen? Crisscross rule. All right, so you put the 2 here in front of the oxygen. You can put the 2 here in front of the magnesium, and you get this, which is wrong, because you need to remember that ionic compounds do not show literal numbers of atoms. They show a ratio. What is the same as a 2-to-2 ratio? 1-to-1. So really is MgO. And you can kind of see that. The charges need to balance out to 0. So if I've got a +2 charge and a -2 charge, that's it. They balance out. So I just need one of each, and it's enough. But try the crisscross rule for any others. That helps. So ignore the sign, just put the 2 here, put this 2 here, and then simplify. Number 8. Which is larger, F minus or Cl minus? Cl minus. So we're looking, you know, apples and apples here. They're both anions, and they're in the same group. We know as you go down the periodic table, you're adding electrons to a larger shell, a higher shell number. So fluorine's valence shell is shell 2. Chlorine's valence shell is shell 3. So you've got more electrons, it's bigger. So Cl minus is bigger. Now, which would have a stronger ionic bond, NaCl or NaF? Anybody want to take a crack at this? Yeah.
It would be NaF because they have a larger electronegativity difference.
That's a good guess. There might be something to that, but let's use Coulomb's law first. So Coulomb's law says that the force is proportional to the charges and the distance between them. So what are the charges on these two?
Don't forget the square.
They're +1, -1, +1, -1. So the charges are the same. So what's the other thing? It's distance between them. So if I roughly drew NaCl, here's Na, and here's Cl, a little bit bigger. And the distance between them, center to center, that's the distance, right? So what if I drew NaF? Well, I'm going to try to draw this the same size. They're the same Na. And we know F minus is smaller than Cl minus. So I'm going to try to draw it a little smaller. Something like that. I don't know how big it is compared to sodium, but that doesn't matter. And if we do center to center, and it's kind of hard to see, but you can hopefully see that this distance is smaller because fluoride is smaller. And if the distance is smaller, if the denominator gets smaller, what happens to the force? It gets bigger. So as your denominator, as the distance gets smaller between them, this whole term gets bigger. The smaller you make the denominator, the bigger the overall term gets. And so the force of attraction between NaF is much stronger than the force of attraction between NaCl. So NaF, according to Coulomb's law, should have a stronger ionic bond. Okay? So we're just using Coulomb's law here. And here is, let me see what we're doing next. I think that was it. Okay. No, we're going to 5 through 8. Let's see. No, I guess we didn't. All right. So, I'm going to skip that because this is too. Well, no, let's skip it. So, we'll come back to this in a second. What is the formula that you're going to make between these two compounds? Don't worry about what they look like beforehand. Just think about what they are, what kind of compound they would form, and what requirements they would have to satisfy. So I'll stop it there. And we'll see what people vote. Okay, we've got equal B and C about. So, K is potassium, and that is a metal. And when you turn potassium into an ion, what ion would it make?
K1.
K1, 1 plus 1, so plus. It's group 1. That's the ion it would form. Now, chlorine gas, this is the elemental form of chlorine gas. When you have a sample of chlorine, this yellowish poisonous gas, every molecule inside that container is going to be Cl2.
Diatomic?
It's diatomic. It's a diatomic molecule. But when it forms an ionic compound, the Cl2 part doesn't matter. What is going to be the ion form of chloride? Like what charge is it going to have? -1. It's group 7. So anything in group 7 as an ion is going to have a -1 charge. Why are we looking at ions? It's a metal with a nonmetal. They're generally going to form an ionic compound. So those are the ions you're going to make out of these two things.
The first two ones.
Yes. So I'll show you in a second what happens to the other one. But that's what these do when they turn to ions. And 1 and 1, which is the crisscross rule, the formula is going to be KCl, and that's it. Now, like you were saying, well, what happens to the other chlorine? This is going to be later in the course, but when you do this reaction, yeah, you're going to have this solid metal reacting with this gas. It's going to make KCl, and that's going to be a solid as well. But this doesn't balance, and so you would do balancing like this. But we don't have to worry about that right now. This is what it's going to make. All right. The fact that it comes diatomic doesn't matter. It's going to split up. It's going to make separate atoms that will each have a -1 charge. Okay. Okay. So O2 does the same thing. N2 does the same thing. They are diatomic naturally, but don't worry about the fact that there's 2 of them. Think about what charge a single ion of that element would have. Okay. So, yeah, the answer is B. So what about this one? Now that you know that. Don't get trapped. Don't get tricked. Don't do it too quickly. Enjoying the first day back at the office. All right.
That was a good one.
So, let's stop it there. And a little better this time. The answer is A. So why is that? I mean, you know, you're like thinking, well, it's Br2. You said not to worry about that. Well, yeah. But remember, what does strontium form when it forms an ion? It's group 2. It's +2 charge. And bromine, when it forms an ion, is still -1. Same as like chlorine. Same as fluorine. And when you put a +2 and a -1, they don't balance out. So you need to have more of one of the other. So do the crisscross rule. Put the 2 in front here, put the 1 in front here. You end up with SrBr2. And that should make sense, because if you have 2 of these bromides, that's where your second negative charge comes from. 2 negatives and a +2, that balances out to neutral. Balances out to 0 charge. Alright, so this is the formula for the ionic compound you would make between strontium and bromine. Okay. If there's any confusion, please stop. So we did this one. Which of the following is going to have a stronger ionic bond?
B.
Yeah, we already figured out it was B. Why is that? Because fluoride is a smaller ion than chloride is. And the smaller your ions are, the closer they can get to each other.
Stronger force of attraction.
And yeah, the closer they are, the smaller the distance between them. And I'm not talking about this distance, you know, like, we're not talking about how close they are from touching. I'm talking about center to center, that distance. So the smaller it is, the smaller that distance is. And the stronger that force is that keeps them attracted. So, what about these? What do you guys think? So use Coulomb's law and try to understand which one is going to have a stronger ionic bond. So, let's see what people thinking so far. Oh, everybody thinks A so far.
Yay.
Excellent. So you guys are all right. Just to make sure, the charges, and I should write them backwards, but do that. This is 2 plus, this is 2 minus, this is 2 plus, this is 2 minus. So the charges are the same. All right, we have to look at the charges. That affects the force. But if they're the same, then we look at the size. Magnesium is the same, but here oxygen versus sulfur, oxygen is a smaller ion. And so MgO is going to have a stronger ionic bond. Yeah?
Actually, sorry, why is oxygen smaller? Because it has like less electrons. So why is it?
So it's got fewer electrons, but it's also got fewer protons. Actually, fewer electrons is the best reason. But look at the shell model for O2 minus and S2 minus. So O2 minus the shell model is a +8 nucleus with 2 electrons in the first shell, and your second shell is full, 8. S2 minus is very different. It's got +16 as the nucleus, but then it's got 3 shells. And the second shell is full, and the third shell is full too. 4, 5, 6, 7, 8. So hopefully you can see O2 minus is just smaller because of that.
Oh yeah. Okay, I don't know what. Yeah.
Yeah, it's fine. We're looking at a lot of different things. Okay. So now, what about? Oh, let's turn that off. What about these two? Which is going to be the stronger ionic bond, NAF or MgO? This is going to be, well, we didn't talk about this yet, but it's a good, you can figure it out. And if not, take a guess, all right? So, most people think, ooh, it's a little bit split. Most people think NAF, some people think MgO. So let's take a look at this, and we're going to figure this out. So, this is section, or model 2, from that same area of connectivity 22. So we're going to fill in this chart, and we're going to answer the questions 9 through 12. So, here we go. Let's do this chart. And I think I'm going to do this. This is going to suck for the people well, everybody's here. I'm just practicing recording for today. So I have a recording going, and it records the whiteboards, and it records the slides, and it puts it all together in one video. It's really only for emergencies if somebody is out with COVID, something like that. So I'm not going to make it available by default. So if you need access to the recording, let me know. But it's right now it's unlisted. So let's complete table 1, and we're going to fill in using Coulomb's law. So I guess in this case we're not going to, let's see. I don't think we're going to use a K here, yeah. Let me make sure we're doing this right. Yeah, I think we're fine. So let's do that there. So the distance, well, let's fill in sodium chloride. So look at NaF. NaF, we have a radius for the sodium cation. Here's the radius for the fluoride anion. That's just basically how big they are. The distance between them, how is that measured? Well, if you've got a sodium that's this big and a fluoride that's this big, and this is the radius of the sodium ion, and this is the radius of the fluoride ion. If you add those two radiuses together, you get the distance. Right? That's what we're doing. We're just adding these two, and we get the distance between the two atoms. And then we're writing down the charges. So Na is +1, fluoride is -1. And if you put that into this equation, and you do a times 10 to the 5 automatically for that, it looks like you get these numbers. Let's make sure that it works. So, there. I'm going to do the first one just to make sure we get the same number first. So Q1 times Q2 plus 1 times a -1 gives you a minus on top, -1 on top, divided by d squared. So -1 divided by, -1 divided by d squared. So 235, squared. And I get some giant number times the negative to get rid of that negative. And I get 1.8 times 10 to the -5. So this times 10 to the 5 gets rid of the times 10 to the -5 that's on my calculator. So that's why you're only writing 1.8. Alright, so I get 1.8, my calculator says 1.81 times 10 to the -5. I would just write 1.8 here. So that's the force. It's just a simple calculation for a force. I think this force has no units. Like, we're going to ignore the units. We didn't put a K in to convert to any specific units. So what all these numbers are going to be able to do for us is we're going to just compare them. That's it. By themselves, they have no meaning. So for NaCl, the charge is +1. On sodium, the charge of the chloride is -1. So if I calculate this, we already know that this is going to be a weaker force. So that should be a smaller number. Let's see. 1 divided by 283 squared is 1.25. So 1.25, 1.2 times 10 to the -5. So that gets rid of that. Okay. So that makes sense. It's a weaker force because it's a bigger ion. Now let's look at MgO. This is the one where everybody was predicting that NaF would be stronger. So the distance between these two, 72 plus 140, is 212. And the charges, it's a +2 for the magnesium, it's in group 2, and it's a -2 for the oxygen, since it's in group 6A. And now when I calculate, I'm going to put in +2 and a -2, 2 times the -2, divided by the distance squared, 212 squared, and I get rid of the negative with that. I get 8.9 times 10 to the -5. So 8.9. So you can see that the force of attraction between magnesium and oxygen is much larger than the attraction between Na and F. We'll do this one real quick. We can talk about what these mean. 184 plus 72. The distance between them is 256. The charges are similar, +2, -2. And then if I calculate, well, we expect it to be weaker because it's a bigger atom. Sulfide is bigger than oxide. So it should be smaller than 8.9. So 2 times -2 divided by 256 squared. And I get 6.1. Okay. So, let's think about what all this means. In which compound is the Coulombic force of attraction greater between NaF and NaCl? NaF. That makes sense because fluoride is smaller, and so the two ions are closer together. I'm going to quickly look at the question a little bit back. Now, NaCl has a melting point of 801 degrees C. Which of these would you expect is the resulting melting point of NaF? Well, NaF is going to have a stronger ionic bond. Right? We already know that because of the smaller fluoride. So, if we think of melting point, what does melting point do? Like, what is when ions or a solid ionic compound melts? What happens? Do you know?
The energy that takes to break the bond.
You're kind of breaking the bond a little bit, yeah. So instead of being fixed, so as a solid, the atoms are fixed in place.
Oh, no, that's gas.
And when you melt it, now the atoms can actually start to move around. And you're basically giving them energy to break that bond, that ionic bond. If they can move around and kind of separate a little bit,
But they're still in the bond though. from
they're
solid to liquid.
still attracted to each
Gas.
other. But
Yeah.
but it's you're starting to break it
Yeah.
when you melt it. So if it has a stronger bond, would you expect the melting point to be higher or lower? Higher, yeah. It should take a lot more energy to melt it. So we would expect the melting point to be higher, 993 for NaF, if NaCl is 801. So melting point 993 for NaF. I'm sorry, my phone is just going nuts. And I should have put it on non-vibrate either. All right, I'm going to come back to this in a second. So,
Oh, okay, sorry. I was thinking about energy. I was like, okay, that makes sense.
well, so the melting point is related to energy.
Yeah.
So the more energy you have, the
The more
more
the
you can
atoms are
break
going to
that
move
bond.
into
Yeah.
them. Okay, yeah.
You're breaking the force between them. So let's look at NGO and MgS. In which compound is the force of attraction greater? So for MgO, that attraction is much, much higher than MgS. So if MgO, which has the higher attraction, has this melting point, 2,800 degrees C, what would we expect the melting point of MgS to be? 2,800 or 4,000? 2,000 should be lower. It's got a weaker bond, so it should have a lower melting point, and it does. So melting point 2,000 for MgS. All right, so let's read the next question. I think that's it. Let me make sure. 12. Yeah, that's it. No, we got one more. So, based on the data, here, let's kind of move this out of the way some more. There we go. So, based on the data in this table and the one we looked at before, which factor, the size of the ions or the charge, has a larger effect than melting point? So, notice that, yeah, MgO and MgS, huge melting points. And they both have +2 and -2 charges, whereas NaF and NaCl have lower melting points, and they both have +1 and -1 charges for their ions. I'm going to go back to this table real quick. Still lining up, that's good. Oh, it's not lining up. Let me get that. There we go.
Nice.
Touch screen's great. So, notice that the sizes are comparable. I mean, they're not super different. They're a little different, but they're comparable. Let's put it that way. They're on the same order of magnitude. They're not like one's not double the other. But when it comes to charge, yeah, in this pair of compounds, the charges have doubled for both ions. So it turns out that charge is a much, much bigger factor in affecting ionic bonding. In the strength of the ionic bond, and affecting the melting point. So if I go back again to that last table, it's not the size, although the size does have an effect. The charge has the biggest effect on the melting point. These two both have a +2, -2 charge in their ions, and so their melting points are so much higher. But, you know, even within that group, yeah, you can tell there's a difference. The sulfur is a bigger ion, and so it's going to have a slightly lower melting point than the magnesium oxide version. But again, charge is more important, okay? So when we're looking in general at ionic compounds, to determine how strong an ionic compound's bond is, first look at the charges, then look at the size, okay? All right. Let's see, we have 5 minutes to go. Okay, so, yeah, here's a new one. Which of these has the higher melting point? These are great quiz questions, by the way, right? You could even do ranking kind of questions. Right? All right. We'll stop there. And ooh, get somebody could see.
That was by accident. It was off, but it when it turned on, I clicked the wrong one.
It's okay.
Because I was clicking.
So
It's
we
okay. I don't record these or something, anything, or I guess I could, but I don't. So the actual answer is A, and the reason NaBr has a higher melting point is because, you know, bromine is the same between both of them, they're the same size, but sodium is smaller than potassium. Sodium is period 3, potassium is period 4. Sodium is smaller, the smaller ions will make the stronger bond, and the stronger ionic bond, the higher the melting point's going to be. So you have two measures of bond strength. I mean, you've got the actual, what is the bond strength? And then you've got melting point as an indicator of bond strength too. So I could ask you these kind of questions 2 ways now. Okay. So here's another measure of bond strength. This is another term, and we're going to use it a little bit. So lattice energy. This is a specific definition and for a kind of ionic bond. And it's not for the regular ionic bond like in a crystal, like in this. So lattice energy is when you, it kind of is. Lattice energy is defined as the amount of energy it's required to both break the bond and turn in your ions into gas ions. So there's a little bit more involved than just breaking the bond. You're actually gasifying your ions. So it's a specific definition for breaking an ionic bond. It's just one of the ways you can break a bond, and that's called the lattice energy. So which one has the larger lattice energy? NaBr or KBr? Sorry, I shouldn't turn that on. So there's no trick here. It's just another way of asking which is stronger. So the answer here is going to be A. All right. The smaller ion, the smaller sodium, creates a stronger bond to bromide than potassium would. And so NaBr is going to have a stronger bond, higher melting point, and higher lattice energy. Because lattice energy is the energy required to break that bond and turn it into gas ions. But the breaking bond part is the key part. So if you've got a strong bond, you're going to have to put more energy into it to break it. So the stronger that bond is, the higher the lattice energy is going to have to be. I'm not going to turn the clicker on for this one, but based on tables 1 and 2, which has a larger effect on melting point, it is going to be the size sorry, the charge of the ions. Charge of the ions. So the difference between these two categories is humongous. And they're based on charge. +2, -2 versus +1, -1. The size of the ions does make a difference, but it's a smaller difference than the charge itself. Okay? So always compare by charge first. Separate out like charges. Compare those individually for size afterwards. Okay. So which of the following has the stronger ionic bond? This is the one we predicted. Everybody knows the answer now. MgO has the higher melting point. It has the stronger attractive force. It's the stronger bond. Okay. We can tell this from Coulomb's law. Again, that K has a negative in it, but in this case, the charges are going to dominate the force in this equation than the distance. The distances are similar. They're different, but they're not that different. But the charges are very different. You're doubling them. How about this one? Which has a higher melting point?
Oh, you gotta square that D.
Oh, you're right. Sorry. You're used to writing the other version.
Yeah.
All right. So, hopefully this is easier now. Yeah, people are starting to get it. The KCl is going to have the higher melting point. It is the stronger bond. And that's because the potassium ion in this compound is smaller than the cesium ion in this compound. You can tell where they are by where they are on the periodic table. Potassium is smaller. It's in period 4. It's only got 4 shells of electrons. Cesium has 6 shells of electrons. It's much bigger. And the chloride is the same. We're not going to give you any weird ones where the cation got smaller and the anion got bigger. Don't worry about that. We're not going to let trick you or anything. It's going to be pretty obvious examples. So what about this one? Which has the higher melting point? So this is why I would get the table of polyatomic ions and start looking at it and reviewing it so that you're comfortable seeing a polyatomic ion and recognizing it. So remember, CO3 is the polyatomic ion carbonate. This has a -2 charge. Think of it as just one giant ion. Key word in there. Okay. So, starting off, we got equal, almost equal votes here. The actual answer is A. So I said giant. It's pretty big, right? It's a carbon with 3 oxygens. That's one pretty big ion. Whereas this thing is just 1 oxygen, just an oxygen by itself. That's smaller. This anion is smaller than this anion. And the fact that this anion is smaller, they have the same charges, right? O is 2-, carbonate is 2-, the K's are plus.
Oh, it is. I messed up.
So the charges are the same, so we're comparing by size. The smaller ions are going to have the stronger bond, and so we're going to have the higher melting point. Okay? So carbonate is big compared to just oxide. And that's it for today. Hopefully your mind is not like, oh my god, I got a lot of work to do.
Is there anything, do we have to bring it on Wednesday? Just
No.
walk into the lab?
So as far, if you have your lab book, bring it. If you don't, that's okay.
Alright.
I'll
And then
try
just-
to make copies of the stuff we need But please try to get your stuff in by next week. If you're having problems ordering materials, let me know. We can work with you. I can work with you.
So should we,
Yep.
sorry, so should we have to workbook homework, for you on Wednesday?
Monday, right?
Monday, yeah, and I'll actually post physical copies of this, and probably the next assignment on D2L so that you can do the homework.
So is the bookstore closed?
I'm sorry?
Is the bookstore closed?
No, it's open. I think the
Oh.
hours are 10 to 3.
Well, I'm gonna go there.
Yeah, everything is here.
It's shortened hours, but it is open.
So
Okay, well,
instead
it's
of,
like on the
ordering it, we
Wednesday.
can just go there?
Maybe. I don't know if they haven't.
We're basic goggles, and we need anything else.
Oh,
Do we need stuff?
That's a good question. Good point. You don't need to bring anything. Just please wear closed-toed shoes and something to cover your legs in case there's splashes. We will have goggles for you. If you are not comfortable wearing the shared goggles, then you'll have to buy your own, and they have to be the full, face hugger goggles. But the goggles we have alcohol wipes, and they always go in a UV cabinet afterwards, so they get semi-sterilized. And I say semi because to get sterilized you need steam as well, which ours doesn't do. But it's probably pretty safe. So, and they're mostly new. They're pretty new goggles too. They haven't been used in. Yeah, we got new goggles for that. I think this lab that we're using I haven't used it yet, so I think it's a different one from last time. Or is it the same one?
I didn't look, I was
Nice
just
to meet you.
saying.
I can't remember.
What's your name?
Miguel.
Okay.
Anyway,
nice to meet you.
what else?
Oh, I don't know how classes go.
There's no pre-lab.
My name's
Yeah, don't
Miguel,
worry about
nice to meet
anything.
everyone.
Just come tomorrow, Wednesday.
Maybe we'll all get to know each other.
So come to the lab on Wednesday,
Maybe you do.
and then we'll have lecture afterwards, after lunch. So yeah, take it easy. If I forget anything else, I'll let you know by email.